Hello, this is John Wen. The title of the talk is Machines Develop Consciousness Through Autonomous Programming for General Purposes. The outline of the talk, I talk about introduction, Turing machines, universal Turing machines, 8 conditions, GENISAMA for consciousness, GENISAMA super universal Turing machines, developmental networks, DN for learning consciousness, motivation, optimal properties proven for developmental networks, consciousness learning examples, early conscious learning examples, and then conclusions. Now, introduction. The subject here includes biological animals and artificial machines. Let us consider questions. Can machines be conscious? Natural systems and artificial systems. In New Delhi, India, a cattle walking autonomously, and I do not see owners next to him. He walked for at least half an hour alone. And a person driving on the motorcycles, and they are doing autonomous learning and learning consciousness in this setting. In terms of the consciousness, we can go back to at least John Locke. He published an essay in 1890. He described consciousness as the perception of what passes in a man's own mind. Let's look at definition of Merriam-Webster online dictionary. It has 5 definitions, slightly different. The first, a state of being aware of something within oneself and external objects, states of fact. Number 2, state of sensation, emotion, volition, thought. Number 3, totality of consciousness state of an individual. Number 4, normal state of conscious life. 5, a state of mental life of which the person is aware. There was a dialogue in Autonomous Mental Development Newsletter 2015. I have a piece. The title is Consciousness for a Social Robot is Not Piecemeal. The host of the dialogue, Janet Wills, stated in post-dialogue summary, Wen takes a different position from the other commentaries, starting from the assertion that all aspects of awareness are tightly interrelated and each cannot function without the others. He calls attention to his brain scale models. Integrative systems are needed in modeling, but we should be skeptical of approaches that exclude progress on understanding the biological subsystems of different neural regions. In fact, when I propose consciousness should be addressed in a holistic fashion, and it's not a piecemeal, I did not include a subsistence, but without understanding the global systems and local system tend to be misguided. But if the local system can explain the global behavior, then the subsystems are useful too. Christof Koch in Scientific Americans 2018 wrote, consciousness is everything you experience. It is this tune stuck in your head, the sweetness of chocolate mousse, the throbbing pain of a toothache, the fierce love for your child, and the bitter knowledge that eventually all feelings will end. From the previous discussion, we can see that consciousness is very vague. If you look at the piecemeal fashion, even from disciplines like biology, neuroscience, psychology, electrical engineering, computer science, mathematics, and including physics, many people said that physics is everything. But from each discipline, we are like blind man and an elephant. Now, we like to make consciousness clearer, holistic, and immutable computational details. And I propose a minimal set of mechanisms that will give rise to consciousness. Turing machines is good in the sense that it has a tape, infinite. There's a read-write head that has scan, so you can have attention, and read corresponding to sensing, write corresponding to the action, and the state from like Q to Q prime is a context, and all those are handcrafted. So the disadvantages is that it's symbolic, like state, input, and the direction motion for the head, totally 5 symbols that are symbolic for each transition. No internal representations, everything is external. And universal Turing machines, Turing machine for a specific task, it's a special purpose, but universal Turing machine is general purposes because in the tape has 2 parts. One is the program, another is the data that the program applied to. So programmer for the universal Turing machines, the purpose to simulate the program on the tape to the data on the tape. So it's a general purpose in a sense that the user can supply any program and the data for any given task. How does our brain get program for each task? My position is that human learn task programs and developmental network that I propose. So it's not tape anymore, it's a real word. And Turing machine red hat becomes sensors like cameras and microphones and touch sensors. Right hat effectors, so you have actions. And the state is represented in effectors. You will see right away later on that state is not internal, not handcrafted, but emergent, can be taught, can be also predicted. So real world contains task programs. So the machine needs to learn task programs from the real world. Now look at the GENISAMA. And what's the minimum set? APFGP need to start from baby time all the way to adult. The GENISAMA is the acronym G for grounding. Grounded in the physical world, E for emergent representations, N for natural representations, I for incremental computations, S for skull closed, A for attentive, M for motivated, including emotion as a special case, A for abstract. So the GENISAMAs, the 8 conditions are all necessary for consciousness because AlphaGo is not conscious because it's not grounded. Hand programming is not emergent. You handcraft symbolic representations of features in the networks. IBM Watson is not natural. ImageNet context entries are not incremental. They don't use incremental learning, not required by the context. All traditional neural networks, including the SOM, SVM, CNN, STM, they're not skull closed. All traditional neural networks are not attentive and just function approximations from X to Y for the input output is not motivated. And just function approximations are not abstract, right? So into abstract rules. APFGP for consciousness machines, I like to refer to 2 publications that address consciousness. One is ARXIV, June the 9th, 2020. Another is ICDL Epiloba Conference. The title is Conscious Intelligence Required Developmental APFGP in October this year. And consciousness requires conscious learning. And consciousness is not just outcome, but also causality. When you learn, you need to be partially conscious. And conscious learning by definition is conscious learning by a biological or artificial machine is that the learner is conscious throughout its lifetime learning. It bootstraps its consciousness from default conscious to increasingly conscious to mature conscious. GENISAMA super universal Turing machines. Representation is very challenging issue. In 14 times, then we can describe APFGP inside DM. The time folds and folds. This is like frame time, 0, 1, 2, 3. And we have active word and with sensible word. and the sensor X area will sense the environment. Motor area will take supervision from the word or emoji itself. Then the scope brain Y can see that this linking is very important because highly recurrent system. But once you're unfolding time, each column 1 will take input from 0, 2 or from 1. So you will never have iteration within each time frame. So it's real time and we avoid many problems like local minima. So if you look at it, the brain part, which is XYZ, then you have a linking from XYZ to next AYZ, and then next. Developmental network for learning consciousness is a general purpose, and we have a developmental network DM. You can consider that if you have a Y have a XYZ, and the time T from T minus 1, then you next time with T plus 1, you can see that you need a 2 time frame to have X effect to emerging Z. But it's not just from X to Z, but also from context. So it's a highly recurrent system from XY, X, from Z to Y to Z, and Y to Y to Y. You can see that extremely complex hierarchical system. And you can have also Z to Z directly. Right now, I only draw Y here. Now, with that one, you have a highly recurrent DM, and it has a occipital lobe, and you have parietal lobe. Then you have effectors here. The effectors can describe type and locations and higher input, and also can take the rules. And from this connection, you can see that each neuron has 6 fields: sensory fields, motor fields, lateral fields, and you have receptive, and you have effector. Combined together, you may have 6 fields. If you look at a simpler form, that's called absence of Y-to-Y connection, then over here, the Y only takes XZ, and that's enough to describe FA. Although it's not the most powerful predictors, but sufficient to prove the general purpose and property of the super Turing machine. And the motivation, we have a serotonin to model pain, stress, threats, and punishment, dopamine to model pleasure, wanting, anticipation, rewards. SH will represent expected uncertainty, and norepinephrine and E will represent novelty or unexpected uncertainty. But detailed model computation, I suggest you look at papers. Now, optimal property proven for DM. DM autonomously learns any Turing machines, including universal Turing machines, to generate a grand, highly integrated GENISAMA universal Turing machine inside it with the following 2 important properties. If it has enough neurons to initialize in real time, then it's error-free because it did not get stuck into local minima even from initialization, because initialization it's a random weights, but as soon as initialized, it takes the top-down input, bottom-up input right away, so it's error-free. If a 5 neuron is already initialized and it's learning, then it's not error-free, but optimal in maximum likelihood. Maximum likelihood, you may see that you don't need to really compare the performance with anybody else, because no system I know that's optimal in this general fashion, and so it's the best performance if you compare apple with apple. Conscious learning examples, there are 2 operation modes: simplified assumption when supervised, like when you are baby walking and you supervise the motor. Unsupervised, when the baby is let free to it can learn consciously, and the learned experience is directed by its consciousness. Now look at the early conscious learning examples experimentally, and we claim consciousness because it's a general purpose. Because a general purpose, then it's not bounded by missing awareness. Everything you designed is not aware by the agent. general purpose is the first general purpose vision, first general purpose audition, first general purpose natural language understanding. And using the same learning agent for the first time for all three sensory modalities. We call it early experience because it's young. And for vision, we have GPS, we have cameras, we have automatic generation of the representation highly integrated and a skill and you teach a system what to do on the fly. And those are the MSU campus way and the training in the blue areas. Then we train internal representations with white-to-white connections in the red areas. Then we learn testing in the dark red areas. And for audition, we do not use MFCC because limited handcrafted representation. We develop Cochlea learning model. And we also, when we do developmental learning, we simulate how the machine learns while hearing because you need to test the voice of the machine self. As far as we know, this is the first time machine learns in real time listening itself to learn pronunciation and recognition at the same time. And for natural language, we have two languages, French and English. This is the representation map onto brain areas, 2D in principal components. And over here is the type. And over here is the language type and concepts. So in summary, AI needs consciousness to get credibility of power. Although so far many researchers intention avoid consciousness. And I think that for machine to be really intelligent, its learning must be conscious. And the GENISAMA universal Turing machine is a minimal set of computational machine necessary for conscious systems. Natural intelligence and artificial intelligence have been unified by the minimum set, and a much exciting practical work remains. Thank you very much.